want it. Okay. To be sure you understand is the concept of standard heat of formation. Standard heat of formation of a substance has a symbolic representation, delta H subscript F with a little circle at the top, like that. That's standard heat of formation. Now, standard heat of formation, by definition, is defined as the gain or loss of energy, heat energy, gain or loss of energy when a substance is formed from its basic elements and their standard state. We talked about standard state elements, and all standard state elements are defined as zero delta H formation. When we look in this table at the end of Ebbing's, this is Appendix C, thermodynamic quantities for substances at 25 degrees. Well, all of the reference tables will be listing at 25 degrees because that's the standard thermodynamic condition. So all tables are built around that. If a departure from that, then it's non-standard and usually some other calculation that are topical issue. But anyway, if we're talking about aluminum here, for example, its standard state is aluminum solid, and it's zero. We come down here to barium solid, zero. That's the standard state. And anywhere you go down here, bromine, you notice that Br2 is a liquid and it's zero. So anywhere you have a zero under the delta HF symbol, it is an element in its basic standard state. Well, elements have variety of forms, and so you'll have several elements. And like bromine down here, it has several delta HFs, but only one is for standard state, and that's Br2 liquid. Compounds sometimes have two different delta HFs if they're in different states. Okay, when we look at water, we've got H2O as a gas is a minus 241.8, and as a liquid is a minus 285.8. So while there's the same compounds, the delta HF for the gas is different than that because they're at different energy levels, like on the heating curve. A gas phase water, steam, will certainly be at a higher energy level and give off more energy, and therefore it'd have a lower number. And then the liquid, it would be a little bit lower, doesn't give off as much energy. But anyway, it doesn't have ice in here. I'm surprised at that. But anyway, for any substance, it will have a number out there, and that number is based on the formation of that compound from its basic element standard state. For water, we'll use liquid just because everybody's used to that. What's the standard state of hydrogen? Well, it's one of the diatomics in gas form. Well, what's the standard state of oxygen? Well, it's a diatomic also, like that. So we write those down, and we put an arrow like that, and we just for grins, I'm going to use a half right there, okay? Half mole. Oh, that's messy. How do we do that? There, looks better anyway. Okay, gives a 1 mole of H2O liquid. Now, these are basic elements forming this compound. So the delta H of formation of water in the liquid form is a minus 285.8 kilojoules per mole. Okay. If I went over to another substance, let's say I want to look at methane, methyl alcohol, OH. Yeah. Let's look at methyl alcohol. You don't have to remember the name or anything like that. But methyl alcohol is made from what? Methyl alcohol is made from carbon, hydrogen, and oxygen. So when we write the basic heat of formation equation for this compound, is carbon is a solid and is graphite. You can look in the back of the thermodynamic table and find carbon by itself, and the one that has a 0 by it is the standard state. We already know about oxygen and hydrogen, so we have to put those down in standard state, H2 gas and O2 gas, and all this is going to form CH3OH, and it's a gas at standard state at 25 degrees. So we have to have a 2 right here and a half right there. Now, it doesn't matter. As long as you got a balanced equation. The delta H of formation, which you'll have to list in a few minutes, I'll show you how to use it, is always 0 for each of these. It doesn't matter how much you have. It's always 0. The only one that has a number is this methanol out here, and that one is a minus 200.7. Now, the elements in basic standard state were assigned zeros because that's a convenience by the supermind out there that makes all these standards and stuff like that. In essence, take the methanol. If we have an energy line increasing, going up right there, and this just happens to be the 0 kilojoule mark. Well, on that plateau right there, you will have carbon, graphite, you'll have your hydrogen in gas form, and you'll have your oxygen in its standard state. And I'm not going to write coefficients for this. It's just that's what they are. They are all zeros. Then you make the compound. Well, it's negative here, and so we will drop down to, say, 200.7 kilojoules negative, and that is for the methanol. So essentially that's what it means. Now, you're not going to have to calculate the standard heat of formation. What you'll have to use is these standard heats of formation. I give you this information back here because that's where it comes from, that you understand what it actually means. It is a formation of a compound from its basic elements and standard. Okay, Hess's law equation is delta H of reaction, standard conditions, because we're going to use standard heats of formations, and so that circle means 25 degrees 1 atmosphere. So just a ID. Okay, it is the sum moles times the delta H of formation of the products minus the sum of moles times delta H of formation of the reactants. Right there. Now the equation may look a little more intimidating than in application, and so I'll show you how that issue comes together right now. Okay, so ethanol C2H5OH, all right, in the liquid stage, and the C2H5OH in the gas phase. We need to, in order to calculate the delta H of the reaction standard state, the one that's hanging out semicolon on the end that's detached, or we put it in the equation. If it's negative, it goes on the right side. If it's endothermic, it goes on the left side of the thermochemical equation, and so forth. We'd have to have the delta H of formations. See how I'm setting this thing up? This one, and then we add up all on the product side, add them all on the reactant side, take the difference between the two. Okay, so the liquid is, we're going to evaporate it, so we got a minus 277.7 kilojoules per mole. And over here we have a minus 235.1. Now, what the equation says, in each of these numbers, once you get the number, you need to multiply each by the number of moles of that substance. Well, there's only 1 mole of this and 1 mole of that. So what we'll do is multiply by 1 mole here, and we'll do the same thing, 1 mole, and so our moles cancel out, and so it's actually 277.7 kilojoules for the reactant side, and this will equal minus 235.1 kilojoules for the product side. Now we'll get some in here in the next one. It'll have some coefficients you'll have to deal with, but this is a good start. Okay, so what is the heat of reaction in this case? Well, it's an evaporation. You could call it heat of vaporization for ethanol, if that's what you were looking for. But in essence, it is the heat of reaction. Products minus reaction, sum N dot delta H of formation of the products minus sum of N dot delta H formation of the reactants. Well, the products are right here. So that's a minus 235.1 kilojoules. I'm going to put a parenthesis around that because that's this term right here. Minus the sum of the components on the reactant side, and that's a minus 277.7 kilojoules. Well, then we apply the algebra to it, and we come up with 277.7 minus 235, minus times a minus a plus. I just switched to make it look better. Kilojoules, and so this reaction, so we have a 46.2 here and 46.2, which you tack on to the end. Now, one last little note here. You can write this equation with the energy number detached like this, and you have to put the sign if you detach it. If it had been exothermic, I'd have had to put a negative in there. But since this is endothermic, I don't have to put a sign. It's just understood to be plus. So here we have C2H5OH as a liquid. And to incorporate this number into the equation itself, we put it on the reactant side. It's going in, energy in. So that would be a 42.6 kilojoules goes to C2H5OH as a gas. So this would indicate an endothermic process going into the reaction right there. Now we'll do one now that has a few coefficients, and we come out with an exothermic values. Let's see. So we're given this reaction, good old down-home rust, iron 3 oxide can be reacted with carbon monoxide, and it will deliver 2 moles of iron and 3 moles of CO2. So now, if we want the heat of reaction on this thing, the delta H of reaction, we first have to look up the delta H's of formation and multiply each one by the coefficient. So we have a 1, and I don't put all the moles and stuff in. When I write a 1 like this and then put the delta H up, that's 1 mole, because it just gets so crowded on the plate, it's almost ridiculous. By looking up the iron oxide, it's 825 kilojoules per mole times 1 mole, and so the number I have here is a negative 825 kilojoules. See what I did? All I'm doing is multiplying by the coefficient. Okay. For carbon monoxide, it's 1 mole times a minus 110.5 kilojoules per mole, and that gives us a minus, 25 is 15, 3.15 kilojoules. Yeah, okay. Okay, so now we need to work with the right side and get the delta H numbers on that. Well, you look up Fe solid in here, it's basic element in its standard state. So I don't even really have to do anything here. I just put a 0. It doesn't 2 times 0 is 0, 0. I mean, just for argument. Okay, and then finally we have 3 mole CO2. So I'm going to look up CO2, 393.5 negative. Yep. Like that, and that comes out to 3 to 5 is 15, 3 to 9, 10, 2 to 9 is 18, 19, 3 to 9, 10, 90.5, looks like kilojoules, negative. Please back me up on there. 3 to 5 is 15, 3 to 9, 10, 3 to 9 is, sorry about that. Anyway, now you identify the reactants and products and then add them together. So here is the reactants, and here are the products. Now, rewriting the entire equation, I usually don't do that, but I knew delta H of reaction is equal to sum of all the products minus the sum of all the reactants. So we'll algebraically add everything together. So we'll start with the products over here. That should be a negative in here, I forgot. Okay, so we'll start with, we have a minus 1180.5 plus 0, minus 1180.5. And I'm isolating this for emphasis, and I suggest you do too, so because it's going to get crowded in here, plus a 0, okay? And then I bracket all that off, and it's all going to come out in kilojoules. So I don't even put the units in at this point. Okay, so that's the product side. Everybody good? Okay. Minus, and then we'll do the same thing with the reactant side. I'll isolate each one, minus 825 kilojoules, and I'm going to add to that a minus 331.5 kilojoules. And then everything, when completed, will honestly come out in kilojoules. So I'm isolating everything to make it a little more visible. Now, apply the algebra through this, and we have a minus 1180.5. I'll drop the 0. Minus times a minus is a plus 825 kilojoules. And then a minus times a minus is another plus. If we commute that negative through, 331.5. And finally, in kilojoules. Okay, so applying the algebraic addition, then we come up with 24 kilojoules. So in this reaction right here, we can go semicolon delta H of the reaction is equal to 24 kilojoules, like that. Okay, this is stoichiometry. Thermochemical equations. Okay. Two NO in the gas phase plus O2 gas goes to 2NO2 gas, and the delta H of this reaction, standard conditions, is given to be a minus 114 kilojoules. Okay, so you start in that capacity. All right, let's say the problem given is what volume of NO2 gas will be formed on reaction of 38 grams of NO gas in an excess of O2, right there. Okay, I'm also putting up here, let's keep it easy. Assume that the conditions are standard STP and that your molar volume is 22.4 liters per mole, okay? If you needed to go to standard thermodynamic conditions, make your calculation at standard and then expand it by the 298 over 273 factor. 298 is 25 degrees. So we'll look at that. It's just a quick calculation. But anyway, the problem asks, we got 38 grams of nitrous oxide and an excess of oxygen. What volume of nitrogen dioxide will be formed? Okay. The rules that I always preach: convert given data to moles, then solve by ratio, equation ratio if you want to say it that way. Equation reaction ratio, and convert back to needed quantity, dimension. I can't emphasize that enough, and students seem to ignore me, and they get on the test and they just get totally lost. Please practice putting that in your mind in terms of working stoichiometry problems. Always go to moles, work the ratio, and then convert it at the end to whatever you need to convert to. Okay, here we'll start with the equation. 2NO plus O2 goes to 2NO2, and we've got 38 grams of this. The formula weight is 14 plus 16, 30 grams per mole. So 30 into 38, 1.27 mole. And of course we've got an excess of O2. Now the equation says we got 2 moles of NO will produce 2 moles of NO2. Since the coefficients are equal, then yeah, this is easy. You don't have to do a lot of ratio stuff. It's also 1.27 mole of NO2 gas yield. Now, we specified we're at standard gas law conditions, so 22.4 liters per mole. And so the volume at standard conditions is 28.4 liters at 0 degrees Celsius, 1 ATM. If you needed to go to a non-standard volume, calculate volume at 25 degrees Celsius or 298 Kelvin. Remember what I told you, it's going from 0 degrees, that's 273 Kelvin, to 298. That's getting warmer. What does a gas do when it gets warmer? It gets larger. So you want to multiply a temperature ratio between 273 and 298 that will make this number bigger. So volume at 25 degrees Celsius is equal to 28.4 liters. Now that's at 0 degrees. I need to make it bigger, so I'm 298 over 273 Kelvin. See, that's a bigger number than if I flip this over, it would make that number smaller. So then, okay, when I use the temperature correction adjustment for hot warmer, it brings us up to a larger number, which is 31.00 liters in this particular case. This equation right there, and let's say you are given 0.0892 mole of hydrogen gas, okay, yields how much energy in kilojoules out of this? Well, the number attached to the equation is just as proportional as anything else in here, okay? If here, look at this. We have so many moles of hydrogen reacting to produce 2 moles of NH3. Well, might as well figure the NH3. So 3 is to 0.0892 is equal to 2 as to X, and X is 2 times 0.0892 divided by 3 mole of ammonium produced. Right there, yield. Well, 2 moles, when 2 moles of NH3 are formed, it will give off, that should be a negative in there, forgot it, minus 91.8 kilojoules. 0.059 mole will give you X, like this. Draw your lines between them, set an equal, and then you have, then solve for X. X is equal to a minus 91.8 times 0.059 divided by 2, and all that's kilojoules. So this will be the energy liberated on the formation of 0.059 moles of ammonia. And we have negative 2.73 kilojoules of energy liberated in that reaction.